So, it turned out that this is a general problem, a generic phenomenon, and the requirements are really straightforward. I mean, I need a 2 or more component field. I need to begin with some continuous unbroken symmetry, but that symmetry can be quite generally. In the case of the robots, it's SO2. In the case of my polariton condensate, it's U1. One can also do it with dynamical systems which have limit cycles. Any non-reciprocal or non-emission couplings. And this includes a whole class of models, predator-prey models, models of flocking, actually dynamical models of neurons, where the 2 component system I have there are excitatory and inhibitory neurons, and your distinction is between systems of quiescence and systems with limit cycles, and indeed, finally, extra polarities. Next, please. So here's my cookbook for actually how to do that. And to unify all of these phenomena, at least as phenomenologists. At the top here, I've defined some generic kinds of models with coupled oscillators, or of interacting neurons, or flocks of birds, or others. These are all described by a dynamical system. If it's a polariton system or a Koldatic system, I'd be talking about something which is a time-dependent Rosbudetsky equation. But there can be other kind of dynamical models. I can look in the vicinity of that model and discover what are the characteristic degrees of freedom. And my models will be separated into models where parity time symmetry is explicitly broken, like the one I just described with the robots, or in fact, in systems where the parity time system symmetry is already explicitly broken, and that in fact would be the case of excitons. And depending on that, I will have 2 kinds of generic phase diagrams, exceptional points of codimension 1, which means lines in 2 dimensions, going from a stationary state to a chiral state, or of points in 2D for the polariton system, where the exceptional points couple regions of coexistence. So one last slide, and then I'll conclude. I've run a long way from where I started, actually. Inspired, frankly, by unrevealed critique and Feynman-like transitions in nuclear physics. Extending that, actually, to thinking about what happens in a system which is open, as an open dynamic system, which has the ability to still, it turns out, have a critical endpoint, but not something which is external equilibrium. And that critical endpoint is in fact, by definition, going to be an exceptional point, because that's the only way that I can form a boundary between different stationary states which can coexist, given that they would then have different eigenenergies. And then, depending on the class of symmetries, I can go between spontaneously broken or explicitly broken systems, and then slightly different classes of this. Now, beyond this, which is where we're doing work now, I described really a new field picture. Everything that you've seen so far assumes that we actually have homogeneous spaces. We know, in general, just like the critical point of a fluid system, that critical point is a point where there will be strong fluctuations dominating the dynamics. And therefore, a universality class of dynamical systems, in analogy to the universality classes that one would have the thermodynamic system at a critical point. And that will, in this system, be a source of pattern-forming instabilities and fluctuations with anomalous scale. And these universality classes are going to be different from those in thermodynamic transitions. So with that, I think I will come to an end of my talk. Thank you, and I apologize for the difficulties with presentation, but I think you've seen the best of it. I would like to thank a bunch of collaborators along the top, so the students, Alex Hadelman, Kyle Callaghan and Judy Weiss in Chicago, postdoctoral colleagues Michel Fouchard and Leo Hanai, and my faculty colleague Vincenzo Vitelli. And it is actually interesting to have, let's say, a collaboration that we've built between people who study quantum phase transitions and people who study soft matter phase transitions. It's fun to be doing that. And some of the earlier work over the years that I've done, I really want to thank former students and postdocs who are all now scattered to various corners of the world. Mishka, Dorothy Keating, Marlene Szymanska, and Francesca Marchetti. And with that, I will stop. And Bikash, I wish you all of the joys of a much delayed holiday and a much delayed birthday. But I'm sorry I'm not with you there in person. But thank you for the inspiration to be thinking about problems like this.
Thank you very much for this extremely interesting talk, which is now open for discussion, and I'm sure you wouldn't mind taking one or two questions, would you?
I'd be very happy to if there are questions.
Okay. Yeah. Why don't you come up and use the microphone?
So thank you for this talk, which has a lot of analogy to what we are doing, of course, studying our phase transition. Now, I was wondering, presumably your first system, the one with the photons and the electron holes, I'm not sure about the second, was macroscopic, meaning it has many electron holes, many photons, so it's a big macroscopic system. Is it interesting, and has it been done, to see how the system properties evolve if you reduce the number of electron hole pairs, if you go from many-bodied to mesoscopic systems, or to systems with less and less particles, to the characteristic change?
Well, I mean, that's actually a very good question. Right? So indeed, what I described is a theory and experiments done on systems that are very large. But actually, there's work underway to make traps and reduce the number of atoms you can run in this trap down to tens or hundreds of those. And indeed, the picture should begin to look something different. One is going to see finite size effects associated with this. Some of the things that you see in nuclei, like shape changes, associated with what I would call in a macroscopic system a pattern-forming instability, but indeed in this, rather than having something which wants to be spherical, would in fact have some kind of clear boundary, and maybe a corona associated with that. That hasn't been done yet, but I think it's going to be possible in the next few years. The challenge, of course, is to make systems that are small and compact, and to make sure that the atoms don't boil off too rapidly.
It's interesting because we have, of course, the opposite challenge to make systems which are big and bigger. We do also find interesting similarities and changes as a function of the number of degrees of freedom. That's why I was asking. So you will be looking at the same evolution.
Yeah, sorry, I'm having trouble hearing it. It's not coming across clearly.
Any other comments or questions? Well, if not, let's thank Professor Littlewood once again. We have missed you here, but you have made up for it with this very interesting talk.
Well, no, thank you very much for having me there. Indeed, I'm very sorry that I'm unable to attend. So I because Calcutta is one of my favorite places, and I would really like to be with you at this celebration. But I'll find a way of making it up to Bikash and others in the future.
Thank you.
So thank you very much.
Thank you. And with that, I think we are more or less on time today, in spite of the technical glitch. So let's break for tea, as announced, and we come back here at 12.